Okay, let's dive straight into this explainer and tackle the absolute final showdown of early physics. You know the drill, right? You start the year strong, feeling confident, but then, bam, you hit a roadblock. Why do so many students hit this wall? I mean, you absolutely crush the early topics like kinematics and Newton's laws because your motivation is peaking. But then you face the real final bosses of the curriculum, simple harmonic motion and waves. Suddenly, the concepts get super abstract, the math gets heavy, and that mental lag just sets in. Well, today, we're going to fix that. We're going to conquer this by opening these concepts up one by one, exactly like a Russian nesting doll. Here is our roadmap for today. Section 1, periodic versus oscillatory motion. Section 2, identifying SHM. Section 3, decoding the phase angle. Section 4, visualizing velocity. And finally, Section 5, the seconds pendulum. All right, Section 1, periodic versus oscillatory. Let's start with the broadest concept and pop open our first, largest doll to look at different types of motion. There is a really important distinction here. Periodic motion is literally any repeating movement over a fixed time period, like the Earth taking 365 days to orbit the Sun. But oscillatory motion, that's a specific subcategory. It strictly demands moving back and forth, to and fro around one fixed point. Think of a little kid continuously swinging back and forth on a playground swing. Now, for that to and fro movement to actually happen, a few rules apply. First, you need a stable equilibrium position. That's a cozy spot where force is zero and potential energy is at its absolute minimum. When you get nudged away from this spot, a restoring force must exist to pull you back. It's kind of like sending a dramatic, "I'm leaving forever" text to your best friend. A true friend is going to pull you right back, acting as that crucial restoring force. If they just text back, "Okay, bye," well, that is definitely not stable equilibrium. Moving on to Section 2, identifying SHM. Let's figure out what actually makes a motion simple and harmonic. If you want to mathematically prove a movement is a true oscillation, here is step 1. The force has to oppose your displacement, meaning we need a negative sign in the equation. But step 2, this is where the magic happens. The power of your displacement, x, absolutely must be an odd number, like 1 or 3. Why? Well, think about it. If you use an even power for your restoring force, like x squared, a push to the left gets squared into a positive, so the force just pushes you further left. There goes your back and forth bounce entirely. We need the math to literally flip directions. And that brings us to the innermost Russian doll. Simple harmonic motion, or SHM, is the absolute simplest case of oscillatory motion. It's an oscillation where the x has a power of exactly 1. No squares, no cubes. Just F equals negative c times x. It's this beautiful direct proportionality that makes the math balance perfectly. Okay, Section 3, decoding the phase angle. Now, this is exactly where a lot of people start to lose their minds a bit. Phase angles basically just tell us where a particle is in its cycle. Check out how these angles translate into fractions of a total time period, t. A full 90-degree move from the center all the way to the edge, that's t over 4. 30 degrees is t over 12. 60 degrees is t over 6. Honestly, memorizing these fractions is a lot like learning the choreography to a Bharatanatyam dance. You're just moving rhythmically through these 30, 60, 60, and 30-degree chunks of time and space. And this reveals a totally mind-bending truth about SHM. Look at the journey from the center point to exactly halfway out, a over 2. That takes t over 12 time. But the second half of that exact same journey, from a over 2 to the full extreme amplitude a, takes t over 6 time. So it takes twice as long to cover the exact same distance. The object does not spend equal time in each half of its journey. It actually slows way, way down as it gets closer to the edge. Which perfectly sets up our next topic, Section 4, visualizing velocity. Let's unpack exactly why that object is hitting the brakes. Let's look at how this changing speed translates mathematically as the object swings back and forth. Right at the mean position, the dead center, your potential energy is rock bottom, but your velocity is at its absolute maximum. Because that restoring force has been pulling you back to the center, you go flying across that middle line at top speed. But at the extreme positions, you hit the brakes. Velocity drops to exactly 0 so the object can actually turn around. And this gorgeous little formula proves exactly what we just said. Velocity, v,
equals omega times the square root of amplitude a squared minus position x squared. If you're at the mean position, where x is 0, your velocity is peaking. But if your position x reaches the extreme amplitude a, you get a squared minus a squared. Boom! The math zeroes out your velocity entirely.
Now, when we visually represent that formula by plotting velocity on the y-axis against position on the x-axis, you might expect a standard wave, right? Nope. Instead of memorizing abstract variables, just visualize the math. Graphing speed against distance creates a perfect, predictable, closed ellipse. It elegantly maps out exactly how your speed peaks at the center and pinches right off to 0 at the edges.
All right, let's wrap this up with Section 5, the seconds pendulum. Let's step away from the abstract formulas for a second and see how this builds the real world around you.
If we take a simple pendulum, the formula for its time period is 2 pi times the square root of its length divided by gravity. By replacing our general math constants from earlier with real-world physical properties, like the actual physical length of a string and the downward pull of gravity, we can predict the exact timing of a swinging pendulum. And this creates what I think is one of the coolest mathematical coincidences in nature. If you make the length of that string exactly 1 meter, something amazing happens. Earth's gravity, which is roughly 9.8, is mathematically almost identical to pi squared. So in the formula, pi and the square root of gravity just cancel each other out beautifully, leaving you with a total time period of exactly 2 seconds.
It really leaves you wondering, doesn't it? How does a simple 1 meter piece of string manage to create the perfect 2-second rhythm that we've used to keep time for the entire world? It's wild that such intimidating, high-level physics is secretly hiding inside every ticking grandfather clock on Earth. So, the next time you hear a clock tick, ask yourself, are you just hearing time pass, or are you actually hearing the universe calculating simple harmonic motion?